different metropolitan cities, they gave a big project, and that basically to demonstrate the technologies to meet the demand. Now, in the last 20 years, precast has picked up quite rapidly in India. For example, even in our campus now, we are doing this precast housing project. Up to 12-story, 14-story people. In fact, in Hyderabad, we have a 30-story precast building.
But again, that volume of dollars or rupees spent on precast construction is minuscule, like 5% compared to the. So that's where I'm wondering.
Well, yeah, that's true. Actually, I think we have to blame it on at least people like researchers like us. The reason is in the US, if you go the PCA manual or PTA manual, you can select your component that you can order.
Right.
Any precaster would give.
That's right.
And we have not reached that stage yet.
Okay.
The standardization still has not happened. We have about, I think, probably 10 or 12 precasters throughout the country. They're doing a lot of projects. But again, we are not able to bring them on board and, standardize all these elements. Everybody is doing it their own way. That's the challenge. If you modularize that, then I think, you can come up with that. That's one thing that we should do. In bridges, people have done it. Because it's all government agencies, they're given standardized sections and, they do it. But in buildings, still we are not on there yet.
When we when we talk of precast, we are not just talking about the shell.
Yeah, okay.
We are talking about a much more integrated precast system wherein you may have core material for insulation.
Yes.
Wherein you may have some kind of ductwork for utilities, wherein you have some kind of even the finishings with the different colors, with a brick finish, adobe finish, whatever finish. So how you put all these together to arrive at a system, and in this process, depending on, now that's only one aspect. The other aspect is the material selection. The third aspect is optimization of these various items to try to put it together. And finally, obviously, you need to bring the unit cost down so that the demand is going to be up.
Now, there is a Bangalore-based company, and even L10, they have also started this 3D volumetric construction with all the finished products. You have a toilet pod with everything is finished, and I said, I have a bedroom with wardrobes.
Right.
Model. So that's but they are not, that volume would be very minuscule.
Minuscule, right.
But the 2D, like you said, planar frames or wall type construction is quite popular now. 3D has just started in India. There's one company they're doing a lot of work, and L&T also implemented it.
So when you say 3D, they make say a bedroom or a toilet or in the factory, and then how do they?
Either they do it in the factory. But let's say if I'm doing it in Hyderabad, I cannot. So what they do, they find a place nearby, they set up a factory there, they produce so that the transportation is easy. Because it all depends upon the location. If it is accessible for transporting the element, they can transport. Now we have long trailers, and cranes are also quite high capacity, high boom cranes are available. But in city area, again, the accessibility is a issue.
You don't use helicopters and things like that?
No, not yet. I don't think. At least not that I'm aware of. Yeah.
I built a bridge in Germany in 4 hours, but it was actually more or less 85%, 90% assembly was done offsite, and the shift by helicopter.
So that we don't know. Now research is going on even the air ambulances, drone-based things.
Right.
that in our own IIT we have colleagues working on that. But scaling up is a challenge. I mean, we are not there yet.
Well, then for that you need a lightweight material and a variety of.
So the drones now, I think that's what I was just listening to one of my friend. He said that body manufacturing is all FRP. See.
You mean the drone thing?
Yeah.
Oh yeah, yes.
So
Because of the lightweight thing.
Yeah. We have a couple of companies that are doing very well. They have been exporting to various other countries as well. So, and they customize it with whatever different sensors you want. So that also, a lot of manufacturing is happening. The last 2 years, I think things are expected to go up. Yeah. But the use of helicopter in construction, I don't think so. We are not there yet. Cost. Still we do it in a very conventional way, cranes. But at least now we are moving away from cast-in-place construction, which is a good thing, because you get a lot of errors during construction, and the prefabricated systems are increasingly used.
See, I don't know, here in US, our waste of construction material based upon the conventional construction is about 1/3, 35% waste of the material.
Yeah.
So if you do this in a manufactured sense, then the waste comes down, the quality goes up, and then you are having a worker working under a comfortable environment, which also improves the productivity. So, yeah. Warren Buffett, a famous man, wonderful guy, he's starting a prefab. He's investing about $500 million or something just for a prefab thing.
I think that's going to come. I remember even you can in Amazon you can order that some.
Those are, yeah. If you talk about things like that, then you have to go to FRP, being a lightweight type material, more flexibility.
Yeah, actually you're right. With all the insulation and things now, see, previously we had a lot of problems with fire, all those things. But G+1, you really don't need to worry too much about fire per se. And if you can have some good insulation, I think it should work. It should pick up.
But these are all built in when a panel or a room is pre-manufactured. They're all, like, think of it like a car, Yeah. I always give an example. If you go to an automotive shop, buy all the components and put a car together, vis-a-vis a assembly line car, the difference in cost is 10 times. So for a building, it may not be 10 times, but definitely 3, 4 times, 2, 3. But that is one part. But the quality goes up. That's the second part, And productivity is up. And human comfort is the other. I mean, comfort means everybody has to work hard. We don't mean you sit in a easy chair and then pontificate. No. But what I mean is a individual can be far more attentive.
Another factor is time.
It's a big factor. Yes.
Time is a big.
Yeah. And the waste, cutting down on the waste.
Now I think everybody is, value engineering, cost optimization. We can cut down the waste.
Right.
25 to let's say 5 or 10, big saving. Right?
Oh, yeah, absolutely. Yeah. So I gave a presentation I have a number of patents in the housing. I gave a presentation to some of the old people in US. They just want to know because they are the ones kind of wanting to downsize,
Well, it's definitely possible.
Go ahead. We're ready?
Yeah, we can start.
Can we start?
Yes, sir.
So, if you recall, If you remember, I said I'll get back to the theoretical part of certain aspects that I did not cover, and then I talked about the design example. Therefore, and yesterday I felt bad in the sense I covered the design, that column design type thing, without talking about the theoretical part. So I thought I will wrap up slide 149 to 198, 199. That's the theoretical part. I'll wrap it up, and then I will go back to the design examples. Okay? All right. So let's start with that. The theoretical part, I told you many times in the course, this is a course, not a R&D presentation. Therefore, you have to pardon me for repeating some of these things. So idea is to make sure certain amount of key salient points are retained by you all. Again, for the details, you may not remember them as well as I do, simply because I've been with it for many, many years. Not that I'm any better, but it's a matter of how you acclimatize yourself to it. That said, I have been talking about strength-based issues many, many times, and there's subsets under the strength-based. Then I also said there is equally important with regards to the service-based checks and balances, and FRPs are primarily driven by serviceability-related issues. So that is why I want to particularly wrap up the impact of service-based checks and balances, even though we have been focusing so far on the strength-based. So we have a couple of other items like extreme events. We are not even going to look into that. These are known as your earthquake type thing. Fire is another. Blast is the third. Hurricanes, you call it hurricanes, you call something else. Hurricanes, yeah. Cyclones, you call it, right? Yeah. Cyclones. So when we talk of hurricanes, we are talking about 140, 150 miles an hour wind velocities, and one needs to understand that the pressure exerted on a wall or on any flat surface is proportional to the square of the velocity. Therefore, as you go up, you are going to have a fairly significant impact coming from the wind load. So those I'm not talking here. Again, when you deal with hurricanes, blast, or earthquakes, that is a dynamic response as opposed to the static responses that we are dealing with. You don't have to know a whole lot of issues about time-based response, except you must appreciate that the modulus or moduli are going to increase if the load that is imparting on a structure is very, very high in rate. Conversely, the modulus is going to be lower if the load application is a sustained value. So the ones of higher rates are, as I said, the wind or earthquake, those are the higher rates, but even a higher rate than that is a blast or a missile attack. So in that case, the modulus goes up with time dependent load. For those kinds of velocity, modulus goes up by about 30-40% because very short durational time. On the other side of the spectrum, the modulus goes down like in creep. normally we would say in an equivalent sense, the modulus is only 1/3 of the static modulus in creep. That's what at least it may not be that simple. Creep is a time dependent, and also it has a different rates depending on the percent of ultimate stress that you are importing for a sustained stress. Keep all that in mind. But for all civil engineering type design purposes, we say if my modulus for FRP is 6 million, the creep modulus is 2 million. That's what the concrete guys do. Remember that. So why am I saying that? The modulus and the I value, EI value, that is the flexural rigidity, as the most critical parameter when it comes to deflection or some kind of a slope related responses. So what does that anything to do with serviceability? That's exactly what it is. Because if you're talking about serviceability, there are 4 or 5 things come to my mind for check and a balance. What are the 4 or 5 things come to my mind? One is deflection. That is, delta is PL cube over 48 EI type thing, whatever. So it is that delta that needs to be controlled. Why it needs to be controlled? Due to excessive cracking, due to human response, due to some kind of a time-dependent increases in stresses. For all these different reasons, that deflection needs to be controlled. That's one kind of a limit state for serviceability. That's only one kind. There are many kinds of limit states. Okay, that is even under that, that limit state varies for different kinds of structures and structural functionality. Two different things. Okay. In the US, the deflection limit state for bridges is L is the span length. Little bit crude, we say, but it works, right? That's all we want. As a designer, not a mathematician, all we want is what works. So, for a typical bridge, the deflection limit state, L is the span length, divided by 800 for interstate highway bridges. Okay, now that is the type of a structure, but if I go with a housing type structure, it is L over 360. So one type is different from the other type, and we have a third type, blah, blah. But this same bridge, I just said L over 800, right? L is the span length. The same bridge, if it is in the rural areas, it is L over 800. If it is in the urban areas, it is L over 1500. So my deflection serviceability limit state has become very stringent suddenly. Why? Almost half. If I'm allowing 1 inch deflection under 18-wheeler type load in rural areas, I'm suddenly saying come to an urban area, it's ½ inch, close to ½ inch. Why? That is where the human response comes into picture. That is where the fatigue and fracture issues come into picture. Why? The ADTT, the average daily traffic or average daily truck traffic, is much higher in those kinds of areas. Therefore, that's one. So it is even more important that people, there may be walkways on the bridges, people may be walking, pedestrians I mean, while the vehicles are moving. So you see, functionality is, the serviceability limit state varies from one structure to other structure. It also varies within a structure depending upon the functionality of it. So that's deflection is one, but it has a lot of other sub parameters associated with it. I just described a couple of them. We can talk on and on and on about that. That's one.
Okay. So the bridges, you're saying that they have more stringent deflection limits, L/800. We also have the same. Probably is it because of the traffic volume that if you allow higher deflections, your fatigue limits will be reached quickly?
Well, that is only one aspect of it. The other very important aspect that we focus upon is the human response aspect. Yeah, I was involved in a bridge, no exaggeration. This bridge, old bridge, 1890s, this is in my town, and nothing wrong with the bridge. There was a light at the end of the bridge, and so people coming from north to south have to stop, whereas there is no light going from south to north. So what's happening is when the trucks are going from south to north, and the people standing with the cars are vibrating too much. So they got scared, so they had to remove the bridge. It's an old-fashioned bridge, in the 1890s. So they put a new bridge to make sure that they satisfied these limits, deflection limit states. That's just one of the several cases. Of course, you have to worry about the deflection limit state so that things like Tacoma Narrows don't happen. I mean, that's another. So it doesn't have to be a Tacoma Narrows, but it could very well be excessive cracking due to, and another one, like you just said, is a fatigue-related issue. We have, of course, a separate set of computations for fatigue limit state check. So fracture fatigue are separate. That's why that is also one of the 5 different checks we are talking about. But yes, fatigue is a very, very, I don't know how many of you, for a long time, if I remember right, for a long time, we did not have a fatigue check for concrete bridges.
Yeah, they're generally better than steel.
They're much better than steel. But now we do have it. That's my point.
Fixed stress, especially, high stress steel can, yeah.
Exactly. We do have that now, So under fatigue, we have about 8 or 9 categories of fatigue for steel. I don't know how much you know. During the World War II, a lot of ships were breaking up into half after so many years of service life, so many miles of service life. And they suddenly found out that the weld is the culprit. When you weld it, you are going to create a huge amount of local residual stress buildups. So again, this is where the serviceability limit state comes into picture. So, okay, I talked enough about deflection. Let me move to another limit state check that we have to do, crack width limit state. That's another, we have seen it, but I didn't explain it well or any till now. So there again, if you're talking about a water tank, you want to have a 0 crack width, right? How do you get that? I mean, by pre-stressing or whatever. So obviously crack width for steel structures may not be very important, extraordinarily important for concrete structures, So that is another limit state. And the third limit state is really the deflection limit state, L over whatever, 360 for buildings or even 240, 800. So the reason I'm saying that back to deflection limit state is that L over 360 or 800 is a misnomer. That was frankly put out, glad they did, in 1860s or 1870s for wooden floors in Britain. So they just kept it. But the real limit state should be a curvature limit state, not a slope type. L over 360 or L over 800 is a slope type limit state, because if I have a 2-foot span bridge versus I can get so much, if I have 20-foot span bridge, I get a much less. So how much is the radius of curvature or curvature? That's why I gave you the other day a limit state from the standpoint of curvature. But we cannot shake out of this conventional thinking that it should be L over 800.
It's physically also more relatable.
So we left it like that, but we caution people to also check. Okay, so that's the third one. The fourth one is human response. So when you're walking, you don't want to feel uncomfortable if the floor vibrates. So typically our human response from the vibrational point of view is codified in terms of the first harmonic or second, first fundamental frequency or the second, those kinds of things. That frequency is, we don't want to exceed that to or somewhere around first one, the first mode, first frequency, to somewhere around 2, 2.5, 3. Then if you can achieve that, wonderful, or else it should be above 6 or 7. This is becoming a big problem for us, because I've shown you one of the pedestrian bridges that I built with FRP, and that, if we don't watch it, most of the pedestrian bridge human responses fall between the human uncomfort zone. Not a comfort zone. Human comfort zone is below 2, 2.5. Once you go between 2.5 to 6, you feel a little queasy, and that zone we want to avoid. That is another serviceability type issue. So like this, we have a variety of limit states, and these limit states also vary for different kinds of material types. Concrete has one kind of a limit state, steel has a different kind, FRP has a third kind of a limit state, so, and wood is another. Something like wood is a fantastic damper within its own material. Therefore, we have a much less stringent limit states for wood. And for concrete, for FRP, crack width related issues, the limit states are much more liberal than. So where do you get the crack width issue with FRP? Where you get it is, if I have a bridge, I have to have polymer concrete on top of it with a gritty surface for rideability and what have you. So we don't want that polymer concrete to crack, which is bonded. That's where you need the crack width. Not for the FRP, but the associated with FRP, that is the wearing surface part of it. So some of our wearing surfaces, believe it or not, are surviving, I would say, millions of cycles of load. So again, that's a material issue. So whenever you want to put a wearing surface, you need to sandblast the top surface of FRP and then place the wearing surface to attain adequate bond. Anyway, so that is so under a given scenario, we have to worry about all these conditions for wearing surface. I already mentioned about deflection. I already given you a number, L over 360 or 240. Again, depends on the function of it, and the flexural reinforcement, distribution in one-way slab and beams. For crack control, I briefly talked about it, but you remember yesterday, I would like to delve on to that a little bit more today, but the message is you need to distribute the reinforcement to minimize any kind of a crack. And the third is, again, that's a serviceability issue. The concrete guys are extremely stringent on the use of shrinkage and temperature. I don't know how much you use. We use 0.0018 times the BD value per foot, you know.
Steel we do 0.0012.
1.2, yeah. We do 180. We are a little bit less. Permissible tensile stress in GFRP reinforcement. Like I said, you have seen that 0.01 is the quote-unquote yield value, and that is what we mean by permissible value. That's a fictitious, artificial number, but again, they tied it to the steel yield, and that works, you know. It may be a little bit more conservative, but it works. There we go. And I'm going to show you in a design example what that comes straight out. Flat roof and floor not supporting structural members, non-structural members, and deflection for service roof loads, rain load, for all those kinds of things where you do not have structural element. Why they say non-structural elements is minimizing the creep related issues. For that, you see how liberal that is, L over 180. Very, very liberal. Normally we don't, our general line of thinking is mostly in terms of L over 360. See what I mean? Now, I want to make one thing extremely clear. Extremely clear. When you talk about deflection limit states, we are only talking about deflection limit states corresponding to the dead loads. We don't talk about those with reference to live loads. Keep that in mind, you know, because the live load comes and goes, whereas the dead load not only stays there, but also it could potentially increase the deflection due to creep.
But some part of the live load also should be considered.
Sometimes people do that as a 20%. That's what they keep calling the service load type thing. We don't. I mean, that's why I didn't want to get into those. Yes, yeah, absolutely. You see, it's easy to add on these things, but the costs of the structure will keep going up. You know, it's a balancing act. So roof, floor, support, likely to be damaged by excessive deflection. If such a scenario exists, that is L over 480 is what we do. Not.
Quick question. These are all including the long-term deflections.
No. Wait. You mean if you mean like say 10 yees from now or whatever.
Basically including the effects of shrinkage.
Yeah, we do not account, I should say, we do not compute deflections for shrinkage. We do compute deflections for creep. Yeah, yes, it includes that. Yeah, not the shrinkage part of it. Yeah. So this is again from the code, section 24.2. The whole chapter 24 deals with serviceability. So this is one. So the above limits are not intended to safeguard ponding. I'm sure you all know what that is. Creep-based delta is separately accounted in the design. The above limit states may be exceeded if measures are taken to prevent damage. So that is up to you as a designer. Shall not exceed tolerances for non-structural elements. Finding deflection using the elastic formula. Considering the eye crack is highly permitted. Haunch properties can be accounted. You know, that type of thing. Okay. So I just read out that using the elastic formula, considering eye crack and moment of inertia, what does that mean? This is what it means. So what we are saying is, here is an equation that accounts for the cracking of concrete elements that are either reinforced with steel or with FRP. And obviously, once reinforced with steel are a little bit less stringent than those reinforced with FRP due to the lower E value. So, this is for, this is the equation, this is an empirical equation. Gerg and Lutz, I don't know how many of you know, it came that was the original Bible for crack control, crack quit. It comes from there. For slabs, again, a more accurate value, but you can downgrade it by having a more approximate value. I'll show you the more approximate one, but I also gave you those equations or those approximate ones yesterday. So these are coming out of these tables from chapter 24. I showed you this yesterday. So for composite concrete construction with FRP, flexural members are shored. Treat them as monolithic cast members if they are shored, right? If they are not shored, what happens then? A part of it is monolithic for live load, part of it is not for dead loads, or part of the dead loads, I should say. So if flexural members are not shored, load paths before after composite action need to be sorted out. And so okay. Again and again, to make sure you control the crack width, here are the equations given. So distribute reinforcement to control crack intention, reinforcement spacing, closest to tension phase. These are empirical rules. Again, there is some science behind it, common sense behind it. Ultimately, there is no formal derivation behind it. The bond factor, they have kept it, unlike in steel-based reinforced concrete, here the bond factor is pretty much kept at 1.2. And this stress in GFRP at service is an equation given right there. The DC is the distance from the tension fiber to the center of the GFRP bar. BCR is the neutral axis depth of cracked section divided by the tension fiber distance, depth. So these are, again, typical limiting crack. I told you yesterday, if you recall, 0.028 is what I use, a more liberal cracking width, which is okay. As far as the buildings are concerned, maybe you need to revert that back to 0.016 if you're talking about bridges and any structure that's open to the environment. So in case of one-way and two-way slabs, distribution of the reinforcement to control cracking is another empirical value. GFRP spacing closest to the tension phase should be greater than or equal to, at the very minimum, 0.026 times that factor. Okay? And the spacing must not exceed the empirical equation given there. And I defined what is C sub C, least distance from the reinforcement surface to the tension phase. That is the clear cover, meaning 1 inch, 1.5, 2 inches, whatever that number might be. Bond factor, like I said, they kept it at 1.2, and all other parameters are defined, and you would see F sub Fs is, I showed this equation in my previous slide, I'm repeating that. Okay. For shrinkage and temperature reinforcement, you can see the reinforcement to resist shrinkage temperature shall be provided in one-way slabs perpendicular. I'm sure those who are teaching the course know that very well. The shrinkage reinforcement are perpendicular to the main reinforcement. Others may not appreciate it, but the idea is somehow you need to have a grid-like mechanism. The main reinforcement in the one that will contain the crack growths and what have you. So now they gave some limitations with regards to less than 3 times H, that is the depth of the concrete slab, or 12 inches, whichever. Again, that also comes from the failure at a 45-degree angle and so on of the crack. Shrinkage temperature stress shall develop 0.006 EF in tension. So really, if you multiply that with the EF of 60 million, for example, 6 million, I'm sorry, 6 million, what you're getting is 36,000 PSI, So the development length, another empirical equation, and all the other items are defined there. Either LD is that, or 20 dB, or 12 inches, whichever is highest. So these are the empiricals.
So in the previous slide,
Yeah.
more previous. Yes, sir, yes. If flexible members are short, treat them as monolithically cast members. And if not short, then it's different. Does it have anything to do with the bonding factor? Like the
No. It is something to do, it should be to an extent what you're saying, but it is something to do with the sustained load concept. That's what it is. And also it is something to do with the I, moment of inertia. Certain part of the load acts composite, other part of the load, meaning the self-weight, acts non-composite. Therefore, you have to differentiate the two. The stresses or the deflections generated by the dead loads of the beam, unshored obviously, is non-composite. Once you combine the two effects, the live load deflections will be behaving as a composite. So that's the most critical part of it. I think I explained that. So the development length for tension terminating in standard hooks, of course we don't have that unfortunately, but they did mention that here, but they do have some mechanical hooks or anchors, remember that, but that's the general equation for the development length. There's nothing much I can explain there except simply saying that was empirically derived based on the experimental data. Permissible tensile stress under sustained load closest to the tension phase must be based on cracked section analysis. And we did see some of that, and as you can see, this comes from the MC over I type thing, where you see M is, that's the stress, M, that is the C part of it, divided by I. The lap splice is not allowed for bars larger than 10. We are not really at this point producing bars larger than 10 for bending purposes, for beams, as I understand. Yes, we are producing double bars that are 2 inches in diameter, but that is not allowed to be placed as a reinforcement for bending or shear or anything. So I think that that statement is might sound superfluous at this point, but in future, if you are going to develop number 12 or 14, or as I was talking to somebody, we even have number what? We even, I think if I'm not wrong, we even have number 18 bar for steel, not for FRP. And those are only used in columns, not in beams, and they have restricted the use of bars beyond, I think beyond number 14 in beams. It's more like nobody would go beyond 12, number 12, which is 1.5 inches, which is about 36 millimeters, you know. So yeah. You have a question? Oh. So the bar beyond the 12 size, 1.5 are not allowed, but here anyway we are restricting it to 1.25 inch, number 10 bar. So we talked a little bit about this yesterday. These are very standard. The spacing, for example, all the 1 inch dB, this is essentially taken out of your regular ACI 318 code, you know. So non-contact splicing, another empirical alert. So the lap splice length in tension, yesterday we talked about the design. I didn't give you these alerts with regards to how much you can provide, and these are all fairly empirical. So please refer to, when you're ready to check and balance these overlap lengths, I strongly suggest please refer to section 25.7 for GFRP reinforcement splice, and some of the limits are given there. Okay. So when you go to the beam column design, and that's why I kind of left it open yesterday. I said I'll come back and redo the design today. That is example number 12, and I'm now giving you the theoretical backup of how you go about doing that. So one step is develop axial bending interaction curve, which we attempted to do. I was unhappy about it. I'm going to redo that today. Developing the axial bending interaction, you saw that, and as of today, the p-value, independent of how much of compression FRP have, is constant as of now. And we have seen that from the interaction curve. And the others, at least you have an idea what goes into it. You may not have the nitty-gritty things, but a broad idea about that. Elaborating the strength reduction factors, we have seen many times. Reforming the shear strength issues, highlighting inapplicability. Please note the word inapplicability for seismic considerations. You know, we don't have one yet. Again, that goes back to simple fact. You need a 3D shaker type, you know, big shakers. You need concrete. In conducting experiments in static is difficult. Think of it, doing it under shaking loads, dynamic load, is that much more difficult. So here are some of the design considerations. 1% of the gross area of the concrete to prevent passive yield. So the stress in compression, modulus in compression is 0.55 FD and 0.8 modulus in tension. And I feel obligated to critique the code a little bit. I believe in a concrete environment, that number is low. Ultimate strain, tensile strain, is, we have been talking about it over and over, 0.01, and that corresponds to your 60 KSI. This avoid unacceptably large delta values. And the max transverse GFRP spacing, very similar, if you recall, to the steel-based design for columns. So it is the least dimension of the column, or 12 times the bar diameter, longitudinal, 24 times the stirrup diameter. So that's pretty much consistent. All these are the limit states that are required to have a proper design. Why do we have this restriction, for example? Because number one, the stirrups give you confinement, but more important than that, if there is a crack, then the crack would at least cut through one stirrup, preferably two, but at least one. You see, if it doesn't cut through two stirrups, a crack that's forming, then you are not going to get the kind of confinement. The confinement is the key buzzword in concrete. Confinement is what gives you the ductility in concrete. So if you don't properly attain that confinement, concrete as a material being brittle will fail catastrophically. Confinement is and that is attained by making sure you satisfy these requirements. Column stiffness, again, I put both of them, meaning steel versus FRP. So for any column, if you look at first order analysis, this is what you follow. So as I said, you need some strengths and stiffnesses upfront to run a first order analysis. So that analysis is done by assuming, this is for steel. Next slide talks about FRP. So that first order analysis is done for beams with 0.535 IG, for slabs 0.25. IG is the gross moment of inertia of the slab or the girder. The steel for the columns, again for steel, that is a cruder approximation, whereas this is a more stringent approximation. I mean, if you want to go in that direction to more stringent approaches, that's fine.
So in beams, we are considering the cracked concrete so that the moment of inertia we are considering less.
That's right. That is called a first order analysis, right?
But when it comes to the column, so the cracked concrete we don't consider. The full section we
That is the problem. What you also look at it, please, that the moment of inertia reduction for columns is much, much less than that for beams, number one. Number two, when you're dealing with the columns are subjected to bending. Maybe small bending, but again, as per the philosophy, we are not getting to the levels of crushing. We are not even getting to the levels of quote-unquote service load thing much earlier than that. So if you look at first columns, for example, please look 0.7. If you look at beam, 0.35. Why is it that it is 0.25 for slab, not for the beam? Why? The function is same, right? Why you have it as 0.25 there compared to 0.35 for beam?
maybe the size.
The size effect. I'm dealing with a column that's 8 inches, 9 inches, slab 8 inches, 9, 10 inches. I'm dealing with a beam that's 20 plus inches. So they thought through all these very carefully. So that's why. So we are presuming upfront a column will have a bending and it will, again, please note, this is an approximate methodology to begin with as a guide. This is not the final say. We are using this to obtain the moments and the other forces and the deformation, and if it works, wonderful. If it doesn't work, you have to upgrade or downgrade things. So this is just a guide. So if you look at the similar type of a thing that I showed you for steel and that of GFRP, you can see how the numbers are stacking up. Obviously, somewhat lower. Yeah, I mean, again, lack of stiffness. And one other thing we'd like to point out to you is if you're going to simply blindly substitute your philosophy of steel onto GFRP, then we are talking about somewhat of a increase in the amount of reinforcement with GFRP compared to steel. Steel, take a look at it. Any of your old designs, if you have exceeded 1.5%, you didn't do a very good job. That's an inefficient design for steel. Whereas here, 2.5 is an average value. So again, there are more accurate approaches and more simpler type approaches. So we talked about this yesterday. I didn't repeat it. Deflection for lateral load is found using 1.4 times the column flexural stiffness. Slenderness ratio, typically KL over R, KL is the effective value. Please note, typically KL over R, they suggest is 22 or below. Then the slenderness effects for compression member may be neglected. Whereas that number is somewhat lower for for GFRP, and for unbraced, of course, it is lower. The KL over R of 22 is probably of the order of 17, 18 for GFRP. For unbraced, it may be 12. This is ACI 318. Please remember, is a steel-based code. Therefore, you have 22, or again, these values are modified whether a column is a single curvature or a double curvature. Obviously, double curvature ones are much more load carrying element than a single curvature ones. And I defined, or code defined, what is M1 over M2. M1 is the moment at the top of a column, M2 is the moment at the bottom of the column. So for a given column, you have two moments at the top and the bottom of the joint, and that is what that is about. So talking about the interaction, very important, column strength under combined loads is found by satisfying strain compatibility. We saw that yesterday. I'm going to repeat that today. Bars under compression are replaced by concrete equivalent area, implying we are not accounting for the higher order strength associated with the GFRP bar in compression, not in tension. Mn, Pn, we saw that yesterday. In the vertical axis, Mn is 0 where Pn is the max. Not so on the horizontal axis where Mn is lower than max Mn. That is because compression, P value creating. Therefore, roughly about 20% or so of Pn value is where you get a max Mn value. That comes from the pre-stressed concrete concept, as you know. Do you follow me? That's why you have that little kink that in that curve that we drew yesterday. So that is equally true. Let me tell you, since I did work in the pre-stressed concrete area, that's equally true even for small presence of moment. There is a small increase in Pn value compared to Pn value where M is 0. But that is so small in that, like 5% or so, whereas here, in terms of Mn being 0, you get some number, Mn or whatever, with a small presence of P value, you get a 20% increase in Mn value. Even though it increases, on the other side, not as much. That's why they would start drawing that as a kind of a straight line. So that is that PN curve. A lot of people use it as a 2 or a 3 segment analysis, depending on how they deal with it. Again, we have to worry about design issue, not the. That's a kind of a parabolic variation there. I'm sure your teacher, your guy must have taught you. Similar thing even in steel columns too. Nothing different. Numbers are different, but the shape is about same. So, MU and PU factors are obviously induced under different load conditions, and the MU, PUs, you need to be very careful of having different phi factors, because under certain scenarios, MN in a given scenario may be in tension failure or a compression failure. Depending on that, your phi factor is different. That's why you need to be careful. It's not just a parallel line drawing down on your PN and MN. Failure by GFRP tension rupture or the concrete crushing. This is a very standard approach over and over. The last line is our design basis, or PM diagram development is based exactly on that. So, from a structural analysis point of view, this is an important slide. This is again given in the 440. What we are saying is simplified methods of continuous beams and one-way slabs under gravity loads are given. What does that mean? That means your M and shear values are defined up front for you. Coefficients, exactly. The coefficients are defined for you, so you don't have to go about doing it. And these definitions of these coefficients are always on the conservative side. If you go about doing a finite element analysis, you get a much lower, I shouldn't say much, some lower value. But the ones you see typically, coefficients are on a conservative. That's what it means. We are assuming prismatic members with U uniformly distributed load. The service load, we are assuming. The coefficient, I think the next slide is, okay, there are the coefficients. Those coefficients I'm going to show you in the next slide must follow, I mean, those are valid only and only if we follow these regulations. That's what I'm trying to say. So we are assuming the members are prismatic and the loads are uniform. The live load is less than 3 times the dead load. Otherwise, you have a skewed phenomenon. And another reason why you say members must be under uniform loading is because we are not talking about loading alternate span, this and that, to bump up the negative moments and things of that nature. That's why you need to keep, if you want to use a simplified analysis, simplified coefficient, you need to make sure you satisfy all these requirements. And what are those coefficients? They're given to you right there. These are, please note, you don't have to remember your conjugate beam method or some other kind of a slope deflection method. You don't have to go to your computer only if you don't want to do all that, you want to get a good quick check. This is what the coefficients recommended by ACI. And if you remember yesterday, we used those two. I don't know how much you remember, WL square over 14, and I think the other is WL square over 10. Okay? So, that's different from shear. And the right-hand side is given for shear. Now the first order analysis, again, what is the first order analysis?
Without considering the pre-delta.
I know, that is true, absolutely. However, the first order analysis implies we're talking about lowering the I value of a beam and the column below that of I sub G. That's what is first order analysis. Now you take a frame, you have a gravity load, you have a wind load, and then run an analysis, however, with lower I values, right? So the moment of inertia for the elastic analysis under factored loads for columns and beams is 0.4 and 0.15 gross value. See how dramatically lowered. Look at that. How small that number is. So you need to keep that in mind when you're running it. This is for failure analysis, not for service analysis. So keep that in mind. So the floor roof moment shall be resisted between the columns in proportion to the column stiffness. We saw that yesterday. I didn't do a great job, but that's what it is. You know, we call them some charts. You call another name for it. You were showing those distribution of how the stiffness ratios are used to get the effective length. Yeah, K value. So the service load analysis has immediate and the time dependent deflections from the gravity loads, and that is well laid out in section 24.2. So you can find immediate lateral deflection using 1.5 times the, as we indicated in the previous slide. So when you account for the slenderness ratios, this is a fairly complicated approach. How do you account for that? The point is, once you find the static values based on the reduced I values, that's one part. Then you have to add the other part due to some kind of a delta deflection effect. This is the first order analysis, including the deflections, okay? So not P delta effects, but some bending associated issues are incorporated in the design. So the way you go about doing that is what is being laid out here. First thing first, that is design column per unbraced. That means KL over R less than, that's where, I think I laid out the steps, all the different steps you must check and move forward. So there are about 8 or 9 steps. So the factored moments are delta M2. What is delta? It's defined right there. So it is this M1 and M2 what you're going to place them at the top and the bottom of the column nodes. So Cm is defined there, M1 and M2, M1 over M2 is negative for single curvature, positive for double curvature. You know what a single and double curvatures are. If you don't, let me know. The Cm value is 1 for column with transverse load applied between supports. So the more accurate definition computation for M2 is PU times 0.6, 0.03, coming from equation 6.6. So if M2 min is greater than M2, then Cm is 1. So here is the delta S coefficient. Again, that's defined, and I will be doing that example today. And you can see that M1, now please see, M1 NS is added to delta S. So this is your moment due to the delta in a static sense. Likewise, M2 plus delta M2S, where delta is defined, and Q is that coefficient. I will show you how to get that Q in a minute. So this is the critical part. Delta, what is delta S? it is a magnification factor. Instead of using P delta effect, which magnifies the moments and the deformations, of course, this is a pseudo approach in terms of how you magnify due to lateral deformation coming from wind or other forces. So this is given. I will run an example today. What is PU? What is PC? I'll run that. But I did define those. PC is found from equation 66442. And the P sub U, sum of all sway resisting column loads in a given story. First story, second or third, and you will get that P sub U. K is found as your effective length factor. In the absence of effective length factor, they suggest you take, for column design in a frame, you take effective length factor K as 1.5 in the absence. But if you want to take K as 1.5 and move forward, fine. On the other hand, if you think the K value is going to come out to be less than 1.5, after the first iteration, you do a couple of more iterations and establish the K as 1.2 or 1.3 or whatever. But if you are lazy, not wanting to do it, just take it as 1.5.
But in using FRP, generally the second order analysis we won't use.
Right, that's not allowed.
But if delta S value is greater than 1.5, then what we have to do?
Right now, the code is saying we don't want to get there because we don't have the data. That is the problem. You see, so please note, I'm not hiding of answering a question, but the code itself is hiding due to lack of experimental data. I can do all I want to do with the theory and the finite element analysis or matrix method, but you have to back it up with experimental info that's absent. So again, all the definitions are given. Beta sub ds is the ratio of max factor sustained shear within the story to max factor shear in the story associated with the same load combinations, you see. So these are the definitions. I'll run an example and I will show you some of that. All these, how they're applied. There is a, I think I defined that cap Q in the previous one somewhere, but that is what that is. And the PC is pi square EI over L square. Effective value, again, please note how dramatically it has been downgraded, 0.24, because of the cracked section. So as I said, I have a lot of admiration for these concrete guys, how they have reduced this very complex cracked design analysis into some of the simpler approaches. The steel guys couldn't do it really, you know. They're all confused about this plasticity aspect beyond the yield, and they hassled with it, and they gave up after a while, you know. Right? Am I right? Okay. Because I know we were doing design for a while, for almost 10 years, both the elastic, ASD, allowable stress design, and the plastic design. Remember, the code had both for about 10 years, or then they quietly dropped out the plastic design approach. But concrete guys kept at it, and that's why they have these reduction factors. So another more accurate approach is perhaps this. So it's entirely up to you to use A or B, where beta subscript DNS max factor sustained axial load divided by max factor axial load associated with the same load combination. Okay. So those are empirical, you have to stay with that. The design approach, for beams and one-way slabs given in chapters 7 and 9. 7 deals with the one-way slab. Chapter 9 deals with beams. So, what's the design philosophy? Which is that the code, as you can see, talks about section 712 and 91. 712 on the one-way slab, 9 on the beams. So we are not talking about voided slabs, we are only talking about solid slab. The reason I say that is I saw a few void slab testing going on downstairs, so you can see that. Why do you use a voided slab? Do you know?
To economize the section.
That's one, yeah. So why void there?
Longer spans.
In the neutral axis portion, the concrete is not necessary.
Right, that is the point. You get it? Why do you remove concrete at that location? Because the effective value of moment of inertia does not decrease much if you have a void there, while in fact you can save 50% of the unit area or weight. Both are same, okay? But more importantly, what does the void do? Two other things. You can run the conduits,
Yes.
right? And secondly, that would reduce noise-related issues. Some dead load reduction, but that would also reduce some of the noise. I mean, these are serviceability-based issues. I didn't say a word about noise, but that's also a serviceability component. We don't worry much. But there are certain building sectors that do worry about that, you know. For example, music theaters, you know, the music halls, they need to be, that's only one component. I was watching the walls, how they are covered with damped carpets. When they receive it, you don't want to have a reverberation, no echo, right? So that's quite a science. One of my colleagues did that. I don't even, if you ask me how do you go about it, I have no clue.
Acoustics.
That's quite a science, really. So anyway, slabs on stay-in-place, non-composite forms, composite slabs constructed or precast, connected to be, all these are included in the code. That's my point. Concentrated load openings are allowed in the design. Beam column slab joints shall be considered as restrained if they are laterally supported on all 4 sides. For laterally unbraced beams, brace spacing should not be greater than 50. So these are the constraints they have provided you in the code to move forward with GFRP. Always you have the design limits for slabs and beams. Minimum slab thickness is same as the beam thickness and satisfying the maximum permissible deflection, which is, I already gave you those, L over 180, 240, 360, and 480. F sub Fs sustained load, that's the key. Now you can define what is the sustained load. Is it just the dead load, the sustained load, or is it the dead load plus 20% of the live load? Typically, we take 20 dead load plus 20% of the live load. And if you have any kind of utilities hung to the ceiling or someplace, you need to account for that. You know, a lot of times people don't realize some of the utilities are hung on the bridges, you know. That's a huge, they're very heavy, particularly the water lines, for example, not the gas lines, but the sewer lines, but the water lines are very, very important, really. So those are the kinds of things. Again, this is again MC over I concept, except that the definition of this is different. And what is the C value? Please note the C value is 1 minus KCR. That is the depth of the cracked concrete. That's the C value. That is the stress. D minus KD, right? That is the distance to the tension side of the cracked beam for GFRP. That's what that is. What is that now? D times this, that is the distance
From the neutral axis to the
Uncurrent.
tension.
tension side. From the neutral axis of the cracked section to the center of the tension reinforcement. So, what is NF? NF is a conversion factor for modular ratio.
1 minus KCR.
So, okay. So what we are saying, oh here. Load? Okay.
This is okay. Clear one.
Clear one, yeah. So what we are saying is that if this is the cracked value, that's the neutral axis of the cracked section, this is KD. Whereas this is D. And it is this distance 1 minus K times D. And please note, this stress that I'm referring to is the stress in the reinforcement. So it's the same MC over I concept, right? Except the C is different. Okay?
What is that? CR?
Correct.
It's a crack. Okay.
Yeah. Okay. All right, next. Effective flange width. I'm sure you all know how the T sections are operated or designed, same deal, except sometimes they have a slightly lower effective flange width, again coming from the philosophy of lower stiffness of FRP than steel. So these are very easy to follow. Even if I read out these, you will forget it anyway. But when you're ready to design it, keep this open in front of you and then establish what the effective values are. For isolated T-beams, flange thickness should be greater than 0.5 BW, that's the width of the beam, of the web, if that's what you want to call it. Effective flange width is less than 4 times B. It's a very stringent value. If you look at it, very small value, nominal value really, more than, this is where they didn't do any testing, but they gave concession for what typically happens under field condition. Beam torsional design, I'm not going to get into that in this class, but overhang shall be neglected, where A square over P less than same as the beam without flanges. Required strengths, we talked about it and we are designing it. This philosophy is what we call this is, I don't know what you call LRFD. You also call LRFD? Okay, you call it limit state. Yeah. So we call it LRFD, load resistance factored design. That's what we call it. You call it limit states. Yeah. Okay. So we have seen this pretty much all along. There's nothing more I can explain here. Sections between the support and the critical section should satisfy the following items, So the limits, we talked about it, 300 over FFU AG. This is a very similar limit state you have for steel. I think that number is different, but it is about the same. Okay, I think it's lower, if I remember right, for steel. So in shear, you can see phi is the factor 7.75, and KCR is what I just showed you today. Whenever I put a KCR, you must have the D factor, that is the depth that is there. So KCR times D is the depth of the neutral axis. Okay, so minimum GFRP spacing is as per section 25.2, and all the others I described earlier shall not be greater than 3 times the slab thickness or 12 inches, all that kind of a thing. Critical section for development of GFRP are max stress location in the slab, wherein termination points need no GFRP. Terminate GFRP where it provides stiffness to satisfy deflection requirement at a distance greater than D or 12. These are rule-based approaches. Okay, sure. I'm going to stop here. I have another 20 slides on the theoretical part. I'll wrap that up after we come back. Then I will take up on the remaining 3 design examples, 12, 13, and 14.
We have 10 minutes break. The tea is ready outside. Please.
Guidelines in terms of when to use and not to use the termination of the bars in the tension zone. That is the key word. My copy, that's okay, is floating around in terms of the design example. All I want to say is there are several editorial errors in that. I'm going to some point to provide them the feedback so that they will make the corrections, but there are many, so keep that in mind. That's all I'm trying to say. So nothing conceptual. Editor.
Unit mistakes and sometimes meter is some units has been.
Not only that, you see, the intent is we want to, let's say, take smaller of the three rules, let us say. They keep calling it higher,
Oh.
I mean, that kind. But there are many other smaller editorial errors. So whoever looking at it, please look at it with a critical eye. Don't take that for granted. I will leave that book with Professor Surya Prakash when, you all can use it. All right. So here are some of the rules that one must follow when you are terminating the FRP bars in the tension zone. Obviously, most important thing again and again and again comes into mind is the flexibility of the bars. So they have, again, these are all rule-based, common sense-based. They are not physics-based. I mean, there's physics behind it, but there's no derivation type stuff in it. Okay, for precast slabs, GFRP shall extend to center of bearing length and a quarter of GFRP as per M max positive into the support or at least. Again, these are rule-based, common sense-based limit states that they have provided. And another LD, that is the lap length type of a thing, or embedment lengths beyond the inflection point are provided. I'm not going to read out, but that's a general idea. So keep that in mind. I'm supposing that you all know what is an inflection point. So, okay, good.